Have you ever wondered what keeps the planets in orbit or why an apple falls from a tree? These seemingly simple questions were a point of curiosity for a man named Isaac Newton, who lived from 1643 to 1727. Newton's fascination with the world around him led to the formulation of his three laws of motion, the cornerstone of classical mechanics. The first law, often known as the law of inertia, tells us that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. In other words, if you slide a book on a table, it will eventually stop because of the external force of friction. The second law introduces the concept of force and acceleration. It states that the force acting on an object is equal to the mass of the object times its acceleration. This law explains why a truck hitting a wall causes more damage than a bicycle. The truck has more mass and therefore exerts a greater force. The third law is famously phrased as, "For every action there is an equal and opposite reaction." This means that any force exerted on a body will create a force of equal magnitude, but in the opposite direction on the object that exerted the first force. But Newton didn't stop there. He also gave us the law of universal gravitation. This law describes the attractive force between all objects with mass. It's the reason an apple falls from a tree and why the planets orbit the sun. Finally, we cannot forget Newton's work on calculus, a branch of mathematics he co-developed. Calculus became instrumental in expressing these laws in a mathematical form, allowing for precise calculations and predictions. In conclusion, Newton's laws provided a framework for understanding the physical world that still holds true for most everyday situations. They allow us to predict with great accuracy how objects will move under various conditions, making them invaluable tools in the realms of engineering and physics. Newton's work laid the foundation for centuries of scientific discovery, and his influence is felt to this day. Imagine a universe where space and time are intertwined, where the force of gravity is not a force at all. Welcome to Einstein's universe. Albert Einstein, a physicist born centuries after Newton, turned the scientific world upside down with his revolutionary theories. His first groundbreaking work, the theory of special relativity, was published in 1905. This theory proposed a radical idea that space and time are not separate but rather a single, unified entity known as space-time. It also introduced the concept that nothing, absolutely nothing, can travel faster than light. Einstein didn't stop there. A decade later, he came up with his theory of general relativity, which provided a fresh perspective on gravity. Contrary to Newton's law of universal gravitation, Einstein described gravity not as a force, but as a result of the curvature of space-time caused by mass and energy. Imagine a bowling ball on a trampoline, causing a dip in the fabric. That's essentially how Einstein viewed gravity. Objects with mass bend space-time, and other objects move along these curves. But Einstein's contributions weren't limited to relativity. He also played a pivotal role in the birth of quantum mechanics, a field of physics that deals with the very small particles in the universe. His explanation of the photoelectric effect, which involves light striking a material and ejecting electrons, earned him the Nobel Prize in Physics in 1921. This work laid the groundwork for our modern understanding of light as both a particle and a wave, a fundamental principle in quantum mechanics. Einstein's revolutionary theories pushed our understanding of the universe into new realms, beyond the limitations of Newtonian physics. His work challenged and expanded our perceptions, taking us on a journey from the very small in the realm of quantum mechanics to the incredibly vast, with black holes and the expansion of the universe. Einstein's universe, a universe where space and time are intertwined and gravity is a curvature in space-time, truly was a leap beyond gravity. Newton and Einstein, both giants of physics, yet their focus and scope of work differed significantly. Newton, with his laws of motion and universal gravitation, provided the groundwork for understanding the world as we see it. His theories explained why an apple falls from a tree, why planets orbit the sun, and why we don't float off into space. He painted a picture of a clockwork universe, where objects moved in predictable ways under the influence of forces On the other hand, Einstein dared to venture beyond the familiar. His theories of relativity introduced a universe that was far stranger and more fascinating than anyone had imagined. He proposed that space and time were not separate, but intertwined in a four-dimensional fabric known as space-time. And this space-time could be warped and curved by mass and energy, causing the phenomenon we know as gravity. Einstein's universe was not one of clockwork precision, but one of black holes, bending light and time dilation. His theories applied not just to the gentle fall of an apple, but to the violent death of stars, to the unimaginable speeds of light, and to the immense gravity of black holes. While Newton's physics is incredibly accurate for everyday phenomena and for speeds much slower than light, Einstein's physics provides a more complete description when we venture into the realm of the very fast and the very massive. In essence, their work focused on different ends of the spectrum. Newton excelled in explaining the ordinary, the everyday phenomena we all experience. Einstein, meanwhile, delved into the extraordinary, the extreme conditions that exist at the very edges of our understanding. While Newton helped us understand the world around us, Einstein led us to the edges of the known universe. Did Einstein's theories debunk Newton's? Not quite. They are more like different chapters of the same book. Each chapter tells a unique story, but together they form a complete narrative of the physical universe. Newton's laws remain incredibly accurate for most everyday situations. His laws of motion and gravity perfectly predict the flight of a soccer ball, the orbit of the moon, or the trajectory of a satellite. Even in the vastness of space, for spacecraft traveling at speeds much slower than light, Newtonian physics still holds true. However, when we venture into the realm of the very fast, the very massive, or the incredibly small, Newton's laws begin to falter. That's where Einstein's theories come into play. Einstein expanded upon Newton's laws, providing a more comprehensive picture of the universe. His theory of relativity, which includes the concepts of space-time and the speed of light, explains phenomena that Newtonian physics can't. Einstein's work on the photoelectric effect also paved the way for quantum mechanics, a field that delves into the behavior of particles at the atomic and subatomic level. This is a domain where the classical physics of Newton simply doesn't apply. So rather than viewing Einstein's theories as a negation of Newton's, it's more accurate to see them as an expansion. They build upon Newton's foundational work, broadening our understanding of the universe to include extreme conditions and scales. From the motion of planets to the ticking of atomic clocks, the legacy of Newton and Einstein is all around us. These two scientific titans, though separated by centuries, have shaped our understanding of the universe in profound ways. Their contributions to science have not only revolutionized physics, but also have far-reaching implications in various fields, from astrophysics to GPS technology. Newton's laws of motion and universal gravitation provided the bedrock upon which much of classical physics was built. His work laid the foundation for understanding the movement of objects, whether they're as small as an apple falling from a tree or as large as planets orbiting the sun. His co-development of calculus remains a crucial tool for expressing scientific laws mathematically. Newton's work continues to be instrumental in various fields, from mechanical engineering to astronomy. On the other hand, Einstein's theories of relativity opened up new vistas of understanding beyond the limits of Newtonian physics. His work has given us a deeper comprehension of the very fabric of the universe, where space and time are intertwined and affected by mass and energy. From black holes to the expansion of the universe, Einstein's theories have paved the way for modern cosmology. Moreover, his work on the photoelectric effect was instrumental in the development of quantum mechanics, which governs the realm of the incredibly small, such as atoms and subatomic particles. His influence extends to technologies we use daily, such as GPS, which requires corrections based on his theory of relativity to provide accurate positioning data. In essence, Newton and Einstein's legacy is the story of human curiosity and the quest for understanding. Their work illustrates the power of the human mind to unravel the mysteries of the universe, from the motion of celestial bodies to the behavior of light and time.